The seminar that I'm going to cover is about the step-by-step process of making GFRC, and it includes a robust from-scratch mix design, so that you'll be able to not only understand what goes into the mix, but how to make it yourself. In this seminar, I'm going to focus on how GFRC works, what the individual ingredients are, how they're used, and the step-by-step process for casting GFRC. Before I really get into the nuts and bolts of everything, I want to share with you some just a handful of photos of pieces that I've done and some of my students have done that are GFRC, and just to whet your appetite as to what some of the possibilities are. Certainly it is a lighter form of concrete. You can do very large things. This is a 14-foot long reception desk countertop that 2 people installed. So it's a very good example of what you can do with GFRC. And the freestanding wall behind it is also GFRC. And there you can see more images of them. So I'm just going to scroll through, not really dwelling on too many of the photos, but you can really begin to see the level of finishes and the possibilities, the design, and the ability to incorporate other elements, water, light, and fire. So just relax, and I'm going to scroll through these and just see some of the pieces that you can do, and some of the ideas that maybe will pop up. This table, for instance, is polished, so you can absolutely polish GFRC, and that's the freestanding monolithic base that was made for it. Water, the fiber optics in there, fire pits. Here's the basic structure of it. Typically, GFRC is cast in a thin shell, 3/4 of an inch to an inch thick, although you can do a massive casting if you wanted to. You could cast it 3 inches thick, although that's kind of a waste of the material, but you could. At 3/4 of an inch thick, GFRC weighs 8 to 9 pounds a square foot, and at 1 inch it's about 12 pounds a square foot. So roughly speaking, it's half the thickness and less than half the weight. And as I mentioned before, the glass fibers, typically the ones we use are 1/2 inch or 3/4 inch long. When the fibers are chopped and sprayed, they can be up to 1.5 inches or even 2 inches long. But because we mix the fibers into the concrete before we actually lay it up, we can't use fibers that are longer than 3/4 of an inch, because they'll fold over and ball up, and then they won't be effective. The whole point of the mix design using such high fiber content is to get a high flexural strength, a high bending strength. And that is the key property that's important that GFRC was optimized for. If you had to spit out some numbers, conventional concrete, forget the steel part, but just the concrete itself, your typical flexural strength is roughly around 600 or 700 psi. GFRC typically is around 2 to 3 times that, and when you incorporate scrim, it can be even more than that. So you have incredible flexural strengths, a lot of flexing that can occur, and it doesn't crack. It not only does it not fracture, but it doesn't even show a crack. So it's very, very beneficial from our standpoint of client, high picky clients, high expectation clients, and people who don't tolerate cracks. That's not to say that you can't make it crack, but it's more resistant to it. Okay, so the way we can make really strong concrete of something thin is we just have to borrow the techniques used for other materials. And if you look at corrugated cardboard or steel studs, where if you took a flimsy piece of paper by itself, it can't support any weight, but if you fold it and use geometry to give it stiffness, then it's possible to make something very strong and stiff without adding any weight. All we're doing is folding the material. And this is how typically GFRC is made. It's a thin shell with molded edges, and those edges give it the stiffness. Now, we use less material, but it's more complicated to make, so that's the trade-off. And so the casting process, instead of simply building a box and filling it full of concrete and having it solid and heavy, we line that box with a thin shell using less material, so it's more efficient, but it's more difficult and we have to be more careful about how we make it. But we can do some pretty cool things with it. So in this case, this is in one of my old offices. We needed a desk, and so I made a 12-foot long desk. It's 30 inches wide, so it's 30 square feet of concrete, and it only weighs 300 pounds. So here we have 30 square feet of concrete that's being handled very easily by 2 people, and they actually posed for this and held it up for a couple minutes. Dave wasn't smiling at the end of that, but you can see how it's not difficult to handle a very large piece of concrete, and even when it's set down, it can be picked up from one end, and it's still very flexible. No cracks. Even after 5 years of heavy use, it had 0 cracks or anything in it. Very, very durable, versatile material. So in the lower left-hand picture, you see that sort of plum-colored or maroon-colored concrete coating the inside of the mold. And that's called a mist coat. And the mist coat is your basic GFRC mix design. It has no aggregate, nothing. It's just a very fine sand, roughly 0.5 millimeter in size, usually no more than 1 millimeter in diameter. And that mist coat is always sprayed in, because that's really the only way you can put it down so thin. And typically it's sprayed in about a 1/16 of an inch thick, no more than 1/8. But typically it's the 1/16 of an inch. It's basically like you're painting the inside of the mold. If, as in the previous example of that aggregate with a 1/2 inch limestone, when you take your mist coat and you add aggregate to it, so you simply add aggregate to it and you mix it up, you now create what's called a face coat. And that face coat is put in thicker. Usually it's about as thick as the average aggregate size, but typically it's about a 1/4 inch thick. And that is, you can't spray that, so you hand pack that into the mold. That would then be ground and exposed. So you either have a mist coat that has no aggregate or a face coat that does. Now, a lot of people just use the term face coat, and although it's technically specific to decorative aggregate, it means it's the part you see. It's like your veneer coat. The backer, in the case of the right-hand picture, the white stuff, that's the GFRC. That has the fibers in it. The mist coat and face coat, they don't have the glass fibers in it. The backer has the fibers, and that's laminated and cast in layers, anywhere from 3/8 of an inch thick up to 1 inch thick or so. But generally, it's put in 2 layers that are each 3/8 of an inch thick, so we get 3/4 inch thick backer layer. So question, do you match the color of the face coat and the back coat? Usually I do, and that's to prevent if the backer gets pushed through the face or mist coat, so you don't see it, because if I pushed white through that maroon, it would definitely show. Usually I only pigment the first backer layer, just to save pigment and money. You don't have to, but you do have to be a lot more careful. So it's sometimes a lot easier simply to pigment it. So it's exactly the same. So your mist coat, here's a mold that was sprayed. You can kind of see the texture and the overall degree. Spraying is a very fast way of applying it. Again, it's only about a 1/16 of an inch thick, and the key to remember is we've just sprayed a very thin layer of concrete into a mold, and now 2 things are going to happen to it. One is it's going to start setting up and firming up, but that happens relatively slowly. The thing we're battling is it's going to dry out, and that's the last thing we want to have happen. We don't want to have this thing dry out on us. So once you spray your mist coat, you better start applying your backer right away. So the key to being successful with GFRC is having all your ducks in a row, being prepared, having all your ingredients already weighed out. I like to mix my first layer of backer first, get it ready, and then apply the mist coat so that I can roll right into it. With a face coat, because you're putting it on thicker, and this is a cafe table where we've lined, it looks like a big pie pan with with a big thick crust. It's a roughly 3/8 of an inch thick, just hand packed with your hands. So you can't spray that. You make it thicker so it sticks, and then the backer's installed in it. So it's actually easier to do. It's less messy. Spraying GFRC, spraying your mist coat does make a big mess. When I was talking about the disadvantages of GFRC and the cost, I mentioned that the two key ingredients are the polymer and the glass fibers. So the polymer its role is as a curing membrane. It permits rapid stripping and better curing and better physical properties. And then the glass fibers are what it give it the flexural strength that lets you make thin concrete, basically. So the polymer of choice in the industry, and this is certainly in the United States, if not worldwide, is a product called Forton. There aren't a lot of GFRC polymers on the market. They're very specialized, purposely developed acrylic polymer made for GFRC. Now there are a lot of different kinds of polymers on the market for concrete. Certainly if you ever have done tile, there are acrylics or latex additives for your thin sets. There are commercial acrylic bonding agents for concrete. Those will not work. Do not use them. They don't have the properties you want. And it's very tempting because you can't go to Home Depot and buy this stuff. You have to special order it. That's the nature of the beast. Everybody has to do that. I have to do it. You'll have to do it. Forton is one of the reasons why it's so universally chosen is because of not just the way it gives the concrete its performance, its curing properties and its flexural properties, but it has a lot of additives, defoamers, it has wetting agents, the way it gives you the surface detail. There are other polymers on the market. Polyplex is another brand that does the same thing in terms of the curing, but the finish you get, the quality of the architectural finishes isn't. A lot of people prefer Forton because of the better surface quality, and for us, the way it looks is everything. So Forton's pretty much the go-to. There are other polymers that are used in concrete. They're not made for GFRC. This particular product has been on the market and been used worldwide for about 40 years. So it's got a huge track record. Proven. Again, it's used inside, used outside. The GFRC was developed to make the outside of buildings, and those buildings could be in Canada, they could be in Mexico, they could be in Saudi Arabia, they could be in Australia, they could be in England, they could be in Minnesota. Hot, cold, wet, dry, bright sun, no maintenance. That's what they're for. And GFRC, because it has a high polymer content and a high cement content, it is extremely water resistant. Water does not go through it, and it's very easy to make waterproof concrete. That's not to say it's stain proof, but it's waterproof. So you can make a tub with this stuff, and it's simply a matter of adjusting the amount of Forton you use in it, or if you're using somebody else's polymer, the amount of polymer. So, question: I have a lot of foaming issues with wet casting GFRC over a mist coat. The foam basically separates and rises to the top, and this leaves a layer that has a lot of holes and causes problems. Can you go through what might be causing this and how to avoid it? Well, it really depends on what polymer you're using. Are you using a defoamer? It could be that you're getting segregation. Really don't wet cast it. It's GFRC. It's kind of like saying I'm gonna buy cherry veneered plywood because I like the way it smells when I burn it. It's a waste of the material. If you're gonna wet cast, use wet cast concrete. That's a very trivial and a bit trite, but GFRC is really geared for other applications. If you're getting pinholes, it probably means you're putting too much superplasticizer, or there's something not right with the mix, and I can't really go into diagnosing the exact cause of it here. But I think you're probably trying to do something that it's not really meant to do. What is the temperature range for casting and curing? Don't let it freeze and don't cook it. 50 degrees Fahrenheit to, let's say, 90 degrees Fahrenheit, or if I had to put a number on it, 10C to 34C. I'm guessing that's a conversion. I've cast in 100-degree temperatures without any issues. You do have to take into consideration the fact that when it's really cold, concrete, GFRC included, takes a lot longer to set and gain strength. And when it's hot, just the opposite happens. It starts setting up really fast. So there are ways, which are again outside of the scope of this seminar, to control that. Okay, so a question from Mark is, CSA cements, which is a non-Portland cement, calcium sulfur-aluminate cement, used with ice and citric acid, which is the retarder, as a mist coat, do they have about the same amount of dry time as when used with precast CSA cement? Well, what do you mean dry time? Not set time. That's different. Drying is air drying. It's drying out, losing moisture. So the answer would be no, it's much faster because it's a thin mist coat. Set time? Basically, yes. It's still concrete. It still sets about the same rate, but you're not fighting set time, you're fighting drying time. So it's something always to be aware of. It's you're fighting the polymer losing moisture, the concrete losing moisture, and that gives the illusion it's setting up, but really bad things are happening because you're losing moisture. Okay, so speaking of moisture, the polymer's main purpose is to retain the internal moisture after it's done, after it's cast and hardens. So if you remember that picture many slides ago where I showed you the big panels that were out in the dirt lot, they're leaning up against posts. Prior to the adoption of polymer as a key ingredient in GFRC, the big commercial GFRC factories would have to cast a piece and then wet cure in a wet room, in a moist room, those panels for 7 days. So let's say every day they make 2,000 or 3,000 square feet of panels. Those would have to be put inside a big wet curing room, and then the next days would go in, and the next days, so they would have to stay in there for a week, and then they could be put on a truck and then shipped off to the job site. With polymer, once that piece cures overnight in the mold, it can be stripped out, and the polymer has now coalesced to form an internal curing membrane, if you will. It's not really a membrane, but that it plugs a lot of the pores, lowering the porosity, keeping the moisture in there. So those pieces then can be set outside, they can be air dried or air cured, and at the end of 7 days of just air curing, they still have the exact same strength they would have had if they had been wet cured for 7 days. So that's the huge advantage of polymer, and that only happens if you use the right amount of polymer and the right kind of polymer. The other secondary benefits of the polymer are that it significantly reduces the brittleness. In structural terms, it's called the modulus. So the higher the modulus, the stiffer it is, the more brittle it is. So if you could imagine like a piece of spaghetti, before you cook it, when it's dry out of the box, it's very brittle. It's a very high modulus. And when you cook it, it gets soft, and now it's very bendable. It's very low modulus. Well, the polymer helps to soften it. So it allows the concrete to flex more without actually cracking. When you have fewer cracks, you have fewer callbacks, you have fewer problems with your customers. So you're more likely to get paid and to keep the amount of money you hope to. So although it's an expensive ingredient, it's a very, very beneficial ingredient. And of course the fibers are essential. You have to have those. The glass fibers are alkaline resistant, developed for GFRC. If any of you are familiar with regular fiberglassing, you know how they make tubs and boats and spas and things like that, or sink molds for concrete countertop industry, those use ordinary glass. Sometimes it's called E-glass or S-glass, and that kind of glass cannot be used in concrete. It will the alkalinity of the concrete, of the cement, embrittles and actually starts dissolving the fibers. And so it was in the early 60s, I believe, that alkaline-resistant glass fibers were developed that would prevent that from happening. And that they have to alloy the glass with zircon, and the zirconia content makes it expensive. Longer fibers give you more strength than shorter fibers, but shorter fibers sometimes are more appropriate for very small, intricate pieces where you're not making a very thick, you're not making a very thick casting, but it's got a lot of intricate detail that you have to go around a lot of corners or anything like that. So sometimes having half-inch fibers is good for small pieces, but generally 3/4 inch are the preferred fiber. And the dosage, they're always dosed the same way, and it's based on the weight, weights of fibers versus weight of, in this case, the GFRC. Now, if you're familiar with the way, say, pigments are dosed in concrete, pigments are an admixture. So superplasticizer are admixtures. Air entraining agents are admixtures. Retarders are admixtures. Admixtures are always dosed relative to the cement content in the concrete. So if you have 100 pounds of cement and you had 3 pounds of pigment, for instance, so 3 pounds of pigment in 100 pounds of cement, you'd have a 3%, 3 per 100 dose of pigment. GFRC is not done that way. The fibers are not dosed. They're not an admixture. It's a very bizarre way of dosing, but that's just the way the convention is. It's 3 pounds of fibers are added to 97 pounds of essentially miscoat to create 100 pounds of backer. So 3% fiber dose means 3 pounds of fibers and 100 pounds of backer that has 3 pounds of fibers in it. And to give you an idea how much fiber that is, ordinary concrete that might use like a stealth fiber they might put in a driveway or floor or patio or something like that, that's 1 to 4 pounds per cubic yard, or 1 to 4 pounds per 4,000 pounds of concrete. So we're using 30 to 80 times as much fibers, or even more, maybe 100 times more fibers. And that's what it takes to make it strong. So we have to use very strong, glass is very strong. It's not very stretchy because you wouldn't want to reinforce with stretchy rubber bands, or a lot of the, like nylon and polypropylene are too stretchy. You need a lot of the right kinds of fibers to do it. And that's the other part that makes GFRC successful, is the fiber.